Hello, and welcome to our discussion of the transport equation. The transport equation is the linear first-order homogeneous partial differential equation of the form a times ux plus b times ut equals 0, where a and b are real numbers, and u is a function of the two real variables x and t. In the past, in ordinary differential equations, we often allowed our coefficients to be complex valued. This time we're going to take a and b to be real numbers for reasons we'll see in a little bit. Let me also remark that in this PDE video and others, I will pronounce partial derivatives like the partial derivative of u with respect to x simply as ux, and likewise ut for the t partial derivative. Our method of solution is to work backward. We will assume that we have a solution u that depends on the variables x and t, and we'll try to see what we can discern or learn about u. And the first thing to do is to recall something from multivariable calculus that we may not think to recall unless we had read the solution in advance. Remember, the gradient of u is the vector gradient of u with ux in the first slot and ut in the second slot. And now we'll reinterpret the transport equation. So 0 is aux plus but. If we look at that sum of those two products for a moment, we'll recognize that as the vector ux, ut, dot producted with the vector ab. In other words, the gradient of u, take the dot product of that with ab, you have to have 0. What does this look like? This looks like a directional derivative for u in the direction of the vector ab. In particular, it's saying the directional derivative of u in the direction of the vector ab has to be constant. And that observation is the key to the following method of figuring out the form of u, which again, I emphasize, may not be the most obvious thing to do. Here's the actual analysis. We are going to fix numbers x and t in the reals, and we're going to define a new function z of s to be z of s is equal to u of x plus sa and t plus sb. So remember what all the letters mean here. X and t are fixed real numbers. A and b are the real numbers that are coefficients from the transport equation. And now s is the variable. S is the thing that moves. And here you see why we wanted a and b to be real numbers. U depends on real numbers, so we need x plus sa and t plus sb to be real numbers. Then we can use the chain rule to calculate the derivative of z. We get z prime of s is ux of x plus sa, t plus sb times a, plus ut of x plus sa, t plus sb times b. But remember, u satisfies the transport equation. So I have z prime of s is ux times a plus ut times b. That has to be 0. So what does this say? The derivative z prime of s is equal to 0. This means that z is a constant function of x. So if you fix your favorite number s0 in R, then you have to have z of s equals z of s0 for all s in R. Let's take s equal to 0. That says that z of 0 is equal to z of s0. But let's remember how we define z. We have u of xt is equal to u of x plus 0 times a, t plus 0 times b. That's equal to z of 0. That's equal to z of s0. That's equal to u of x plus s0a and t plus s0b. So what is your favorite s0? Well, for the purposes of this problem, we're going to pick it to be something special. Let me add an assumption for now. We'll assume that b is non-zero. So our coefficient b from the transport equation is non-zero. We'll work things out when b equals 0 later. Then let's define s0 to be minus t over b. So b is not 0 means we can divide by b. Remember, we fixed a time t a while back, So now we're just putting S0 equal to minus t over b. And that tells us that z of S0 is u of x plus minus t over ba, t plus minus t over b. And if you look at what happens in the second slot, the b in the denominator cancels with the b in the numerator, and this turns out to be equal to u of x minus at over b, 0. So z of S0 is equal to u of x minus at over b, 0. Chaining through the previous equalities, we have u of xt equals z of 0 equals z of S0, and z of S0 equals u of x minus at over b, 0. So this says that u of xt is equal to u of x minus at over b, 0. Or, if you like, I could rewrite that as u of bx minus at over b, 0. What does this mean? It feels like we've just danced around with a bunch of symbols, and we've gone from having a function u of xt that solves a transport equation to forcing u of xt equals u of bx minus at over b in the first slot, 0 in the second slot. How is that at all helpful? We start with the solution u to the transport equation. We find the special relation for u. So let's define now a new function. I'm given a solution to the transport equation at the start, so let me write f of capital X equals u of capital X over b, 0. Then f is a differentiable function of the variable capital X, because u is differentiable in its little x variable. And, gloriously, I can write u of xt equals f of bx minus at, thanks to the relation for u that I have. What does this mean? U of x and t really can be written as f of bx minus at for some function f of a single variable. So go back over the logic again. We start with the solution u depending on x and t to the transport equation, still assuming b is non-zero. And we can find a function f that depends on the variable capital X, such that u of xt is equal to f of bx minus at. This means that we have completely determined the structure of solutions to the transport equation when b is not equal to 0. All of them have this form that I'm calling star. All of them can be written in the form u of xt equals some function f of bx minus at, where f depends on only one real variable. You can ask a couple questions about this solution. Perhaps the first thing is, what happens if b equals 0? We needed b to be non-zero in order to divide on the previous slide. Well, in this case, let's assume that the coefficient a is non-zero in the transport equation. Otherwise, both coefficients are 0 and the equation automatically holds and there's nothing to do. So our simpler transport equation is now aux equals 0, and that just means ux equals 0. So that means that u is constant in x, but u also depends on t. So let's write u of xt equals capital C of t for some function c of the single variable t. Now let us rescale. We'll define a new function, c tilde of tau will be c of minus tau over a. And we can do this because we're assuming a is non-zero, so we can divide. Then we have to have u of xt is c of t. And if we do a little algebraic sleight of hand, c of t is equal to c of minus at over a. The two a's cancel, the two minus signs knock each other out. So this is equal to c tilde of minus at. And remember that b is 0, so this is c tilde of 0 times x minus at, which is equal to c tilde of bx minus at. So are we done yet? Not quite. There's still more work to do. For both the b equals 0 case and the b not equal to 0 case, we assumed that we had a solution u to the transport equation, and found that we could always write u in the form u of xt equals f of bx minus at for some differentiable function f equals f of x. We had to do this in the separate cases b equals 0 and b not equal to 0, but we could always do it. Now, if we start with defining a function u of xt equals f of bx minus at, where f depends on the variable capital X and f is differentiable, then the question is, do we have a times ux plus b times ut equals 0? And the answer is yes. The multivariable chain rule helps us calculate this, and I will leave this as a practice problem for you. This is often how we solve PDEs. We work backward to show that a solution has a specific form. Maybe we do something unjustified or something formal or something symbolic. We get a specific form of the solution, and then we actually have to go in and grind out the calculus to show that this form solves the PDE. All the work we did in this problem was assuming that we had a solution to the transport equation and then figuring out the special form u of xt equals f of bx minus at. Actually verifying that this form solves the transport equation is a somewhat underwhelming exercise in the multivariable chain rule.